Few weeks ago I ordered a magnetic levitation kit just out of curiosity. I wanted to see how it's built and understand the basic idea behind its levitation. So I took it apart and went through each component to see how the circuit is arranged. Even though it's a simple design, the way it keeps balance is surprisingly precise. Magnet is a material that produces a magnetic field, invisible force capable of attracting certain metals like iron, nickel, cobalt, and interacting with other magnets. This field always flows from the North Pole to the South Pole outside the magnet, creating regions of attraction and repulsion. Magnets can be either permanent or electromagnetic. Permanent magnets are made from materials that retain their magnetism even after the external magnetic field is removed. Common examples include neodymium, one of the strongest types used in Maglev systems, hard drives, and electric motors, where compact but powerful magnetic fields are needed. Samarium cobalt, known for its heat resistance and stability, often found in aerospace, sensors, and precision instruments that operate under high temperatures. Alnico, a stable alloy of aluminum, nickel and cobalt, typically used in loudspeakers, guitar pickups and measuring devices, where consistent magnetic performance is essential. Ferrite, a ceramic magnet that is inexpensive and corrosion resistant. Widely used in motors, transformers, and magnetic cores for power electronics. Electromagnets generate a magnetic field only when electric current flows through a coil, usually wrapped around a soft iron core, and are used in maglev systems, relays, cranes, and MRI machines when the magnetic field must be switched or adjusted dynamically. This magnetic levitation kit works without any microcontroller or digital control. On the top is a strong neodymium magnet that floats in the air. Below it, the base has several copper coils and one big ring magnet made of metal and magnetic material. The ring magnet creates a constant magnetic field, while the coils help fine-tune the balance. Together, they keep the top magnet floating by balancing magnetic force and gravity. When the 12-volt power adapter is connected, the power first passes through a small thermal switch called KSD 9700, which is rated 65 degrees and acts as a temperature-controlled protector. Inside the thermal protector is a thin bimetal disc that reacts rapidly to heat. It works on the same principle as a bimetal strip, two metals with different expansion rates bend or snap when heated. At normal temperature, the disc stays relaxed and the internal contacts remain closed, allowing current to flow freely through the circuit. When the temperature reaches about 65 degrees, the bimetal disc suddenly snaps, separating the contacts and instantly cutting off power to prevent overheating. As the system cools down, the disc returns to its original shape, the contacts reconnect, and the power is automatically restored. In other words, it doesn't trip like a fuse. It is a resettable thermal switch that cycles on and off depending on temperature. It is connected in series with a positive DC line right after the input jack and before the capacitors. Its job is to protect the coils, transistor and amplifiers from overheating if the magnetic levitation system is overloaded or left running for too long. On the board there are 4 220 microfarad and 10 volt electrolytic capacitors. They do not filter the entire 12 volt rail, instead they form a local bias and stabilization network for the analog control section. Their role is to smooth small variations and maintain a steady reference. In this design there is no large reservoir capacitor on the board. Most of the bulk filtering occurs inside a 12 volt adapter. The first measurement was taken at the power input. The adapter supplies about 12.6 volts DC with a ripple of roughly 1 volt peak to peak. That's typical behavior for a small switching power adapter under load. When viewed in AC coupling mode, the ripple becomes more visible, about around 800 millivolts peak to peak. It's a clean uniform noise pattern, confirming that the adapter's internal capacitors are doing most of the smoothing. When the magnet isn't levitating, these capacitors sit about 1.18 volts with a ripple of roughly 0.37 volts peak to peak. The control loop is mostly idle here, only making minor corrections as it waits to detect the magnetic field. Once the magnet starts floating, the DC bias rises slightly to around 1.30 volts, while the ripple remains close to 0.37 volts peak to peak. That small increase in bias voltage shows the feedback loop becoming active. The small oscillations in the waveform represent the system's fine real-time corrections that maintain stable levitation. Together, the input stage and these local capacitors form the foundation of the entire system, filtering the incoming power, creating the analog reference and stabilizing the voltage for the amplifiers and sensors. This part of the circuit uses 3 HW101AG Hall sensors positioned between the 4 coils. Each sensor is based on indium antimonide, a highly sensitive material that responds to changes in magnetic flux. They operate in constant voltage mode at around 1 volt and generate a tiny differential output voltage that varies with the strength and direction of the magnetic field. Each Hall element has 4 pins. Pins 1 and 3 power the sensor, while pins 2 and 4 provide the output signal, the actual Hall voltage. In a steady magnetic field, this voltage stays nearly constant, but as the magnet moves closer or farther away, the voltage shifts by a few hundred millivolts. Those small variations carry all the positional information needed for the control system. The 3 sensors work together continuously, detecting how the magnetic field is distributed across the coils. When the magnet drifts slightly toward one side, the Hall voltage from that sensor increases, while the others drop. This forms a closed analog feedback loop that keeps the magnet centered and stable. The operational amplifiers compare these differences in real time and instantly adjust the current in the corresponding coils. This blue component is Baoter 3296 precision trimmer potentiometer. It defines mid-bias voltage for the analog control section, roughly half of the 12-volt supply. I soldered the probe directly to the center pin, the wiper, which carries this reference point. Here the measured voltage swings between 5.4 and 6.4 volts, giving about 1 volt peak-to-peak ripple. That ripple doesn't come from the power adapter, it's generated by the feedback loop itself. As the operational amplifiers continuously correct the current through the coils, they slightly modulate this bias point. In other words, this small oscillation is the signature of the control system working in real time. When the trimmer is properly adjusted, the bias stays near 6 volts and the magnet hovers stably. But just a few turns on the screw shift the balance enough for the loop to lose equilibrium and magnet drops. After Hall sensors and the trimmer, the control signals go into two LM324 amplifier chips. Each LM324 chip has 4 separate amplifiers built inside and can work from a single power supply between 3 and 32 volts. In this levitation circuit, both chips are powered from the same 12-volt line, pin 4, and connected to ground, pin 11. Each amplifier receives a differential signal from one Hall sensor, where the raw output amplitude is typically between 10 and 50 mV, depending on the magnetic field intensity and distance of floating magnet. These voltages are far too small to drive the control system directly, so the LM324 stages amplify them by a factor of roughly 50 to 150, depending on the feedback resistor configuration. During operation, each LM324 channel continuously compares its input, in this case Hall signal, with the mid-bias reference defined by the trimmer potentiometer. When the magnet shifts slightly in position, the Hall voltages changes by only a few tenths of millivolts, but the operational amplifier LM324 instantly reacts, producing a several-fold correction at its output. This feedback modulation, typically around 1 volt peak-to-peak at several tens of kilohertz, represent the active stabilization of the levitation system. After the amplifier stage, the processed signals are sent to the CD4066PM bilateral switch. This chip contains 4 independent electronic switches, each capable of passing both analog and digital signals in either direction. That's why it's called bilateral. Each switch behaves like a small transistor pair that closes or opens when a control voltage is applied. When the control input goes high, logic 1, the switch conducts and connects its two signal pins with a typical resistance of about 125 ohms. When the control input is low, logic 0, the connection is broken and the resistance rises to several mega ohms. A sinusoidal signal was applied to pin 1 of the CD4066 bilateral switch, and the output was measured on pin 2 using the scope in order to confirm the correct pin configuration and verify the signal path through the switch. In this circuit, the bilateral switch works as a signal router between the operational amplifiers and the transistor pre-drivers. The control lines of the CD4066 are driven directly from the LM324 amplifier outputs, which means operational amps decide when each switch turns on or off. By gating amplified whole signals this way, the circuit can dynamically control which coil pairs are energized, keeping the magnetic field balanced on all sides of the floating magnet. Because the CD4066 passes analog voltages directly, it doesn't distort the signal or introduce delay. It simply acts as an electronic bridge that opens and closes in microseconds. After passing through the bilateral switch, the control signal reaches the transistor pre-driver stage. These small NPN and PNP transistors do not drive the coils directly. Instead, they shape and buffer the operational amplifier's waveform before it reaches the large power transistors. The scope capture taken on the collector of the NPN pre-driver shows a strong high-frequency control waveform of about 10 volts peak-to-peak, oscillating around 30 kHz. This is the fully amplified signal coming from the LM324 and gated through the CD4066. A second measurement taken on the base of the pre-driver shows a much smaller waveform, only a few hundred millivolts. This is exactly what I expected. The base emitter junction of an NPN transistor clamps the input to roughly 0.6 to 0.7 volts, preventing the high voltage waveform from appearing at the base. The pre-driver simply converts this small control voltage into appropriate current needed to switch the main output transistors. From here, the pre-driver feeds the bases of the large NPN and PNP transistor pairs mounted next to each coil. Each coil has its own driver pair, allowing the circuit to push and pull current through the windings rapidly and with enough power to generate the magnetic field required for levitation. These fast voltage swings routed through the CD4066, shaped by the pre-drivers and amplified by the final transistor stage, are what keep the coils dynamically balanced and able to hold the magnet in mid-air. With every stage examined from the power input and thermal protection through the bias network, whole sensors and trimmer, all the way to the LM324 amplifiers, the CD4066 switch, bilateral switch, the pre-drivers and the final push-pull transistor pairs, the complete signal path of the magnetic levitation system is now fully mapped and verified on the scope. We traced how a tiny change at the whole sensor's growth through each stage of amplification and switching becomes a high power waveform in the drive transistors, and finally turns into the magnetic forces that keep the magnet floating. This brings the entire analysis to a close, full end-to-end teardown of how this simple analog circuit achieves stable magnetic levitation.